About 3 years now. Before that, I was at Yahoo, where I was working on Hadoop, HDFS and security. I'm a Hadoop committer and PMC member. Since I've been at LinkedIn, I've been working on Hadoop there, as well as Hive and Giraffe, and pretty much anything having to do with the Hadoop ecosystem. I'm on Twitter at BlueBoxTraveler if you want to follow me. I really like taking questions. So let's go ahead and talk about LinkedIn for a second. Everybody here has a LinkedIn account, right? Okay. So at LinkedIn, we're a very big site. There's a lot of things that we would like to do better than we're currently doing. Among those is provide you with timely, relevant news. So you go to LinkedIn, the main thing that we show you is your news feed, and we show you a lot of stuff about who's been connected, who's got an updated profile, if Eli Reisman has an updated profile for Apache Project. We want to make sure that those stories that we get to you are both timely and relevant. Another thing is we have a lot of search engines that we run. You come to LinkedIn and you can search for jobs, you can search for other people, you can search for other groups, you can search for pretty much all kinds of things. And we have to build indices for those. We have to facet them every which way we can. So we want to be able to get the information when people change jobs, when people post jobs, into those indices as quickly as we can. And finally, LinkedIn is a very data-driven company. Every machine is generating a ton of metrics. Every application is generating a ton of metrics. We want to be able to take those metrics and basically sculpt them into different shapes so that we can actually make sense of that raw data. This is just one of our many, many dashboards that glitter the entire canvas. What tools do we have to accomplish these goals? Well, there's two ways of looking at. There's a way of looking at our tools in two ways. One of which is latency. How quickly does that tool work? On the one hand, we have RPC. So that's supposed to return instantly, if not instantly, within a few milliseconds, right? So that limits what we can ask. There's a few questions that we can ask, and we can ask them very quickly. On the other side of the spectrum, we have Hadoop, which I love, but of course, you ask Hadoop, it gets back to you later, possibly much later, possibly much, much later. So we needed a tool that would give us something between these two, and that's what Apache Samza is trying to do. Rather than instantaneous or tomorrow, we're going to try to get back to you within milliseconds to minutes, usually minutes. So this is what we invented Samza for. So as a way of explaining how Samza works, I'm going to go ahead and compare it to classic Hadoop. It's a good way to compare and contrast. I call it classic Hadoop because now, with Hadoop 2.0, with Trunk coming along, what used to be Hadoop no longer is. What I'll be talking about is when we had simple HDFS and federation of that, when we had simple MapReduce, Yarn or anything like that, and we can compare them that way. The first thing that we'll look at is the storage layer. Both systems need a place where they can keep their data before and after their processing. For Hadoop, that's HDFS. For Samza, that's Kafka. How many people here are familiar with Kafka? We're going to go more into depth about Kafka as we go. The next thing is the execution engine that actually runs the computation. For Hadoop, of course, this is MapReduce. For Samza, we are using Yarn, which is then confusing because Yarn is the next generation of MapReduce, but we'll show how that works. And finally, and maybe the most interesting part, is the API that you use to actually get stuff done. Inside of Hadoop, you have your mapper, you have your reducer. They take keys and values, play with them, output new keys and values. With Samza, it's a little bit simpler. We just have one API, process. That, again, takes a key and value, basically, gives you another key and value. So we'll look at each one of those sections. Starting with Kafka, the storage layer. Apache Kafka was developed at LinkedIn starting about 5 years ago. It was open sourced and given to Apache about 4 years ago. It is a persistent, reliable, distributed messaging queue. And we've got a shiny new logo. It took us a while to get that. So we'll look at how Kafka actually works. At LinkedIn, we are using it extensively. We are processing 10 billion messages a day, writing 10 billion messages. We are actually sending 60 billion or more messages a day. This slide has to get updated constantly. And at peak, we're dealing with 172,000 per second. So Kafka is something that we're using. It's very much in production. A lot of other companies are using it as well. It's a successful open source project. Yo.
So if your number is correct, so how many Kafka clusters is
that is per average on one machine.
So on the one node.
We have lots of Kafka clusters all over the place. I don't know how many actually have. Quick aside before we get into the details here. I'm going to be talking pretty much exclusively about Kafka because it's what Samza was built around. But Samza is a pluggable system. In the same way that Hadoop is actually programmed against file system, which is a generic interface for writing file systems, and therefore you can then run Hadoop on top of Amazon's S3, on top of MapR's file system, whatever. We're pluggable as well, and you can run on top of other streaming systems. We know that you can do this because at LinkedIn we're already running on top of a couple systems that we have there. Espresso, which is a key value store, which should be open source soon, but I don't think it is. And another one called Databus, which is already open source, which is a distributed change capture system. So even though Kafka, if you have other things that can be made to look like a stream, no problem. Specifically, we are very much looking for contributions from other users. HDFS would be a great one to have, ActiveMQ, Amazon SQS. We're open source. We want help. If you want to contribute any of these, that'd be great. So, Kafka in 4 bullet points. In Kafka, there are producers that send messages to brokers. These messages can be whatever you want. Kafka is byte agnostic. You send it byte arrays. Those messages have keys and values because this is big data, and everything in big data is a key value. The broker's job is to store those messages, and they store them for a relatively long time. Unlike in most messaging systems where once a message is consumed, it goes away. In Kafka, a message will stay around for either a certain amount of time, a week, or until the log that message that contains that message grows to a certain size. So we will roll the logs over to make it 2 bit. And finally, it's up to the consumers to actually pull the messages from the brokers, rather than in other messaging systems where the brokers or the publishers are pushing them to the consumers. The consumers can come back and say, I want the latest message, I want to start at the beginning, I want to start in the middle, I want to replay, I can do whatever I want. All the logic is actually controlled by the consumers. It lets us do a lot of things. Kafka topics, you can look at an example one. Status update event, something like a Twitter or a newsfeed. It has a key. In this case, we can say the user ID of whoever updated their status, and then the value, whatever we want. As people put in new status updates, we will just append these messages to the end of the log. The other thing to know about Kafka topics as we go is that they're partitioned. On the key by default, but that's all portable. So we use hash partitioning in general. So in this case, we expand and grow the topics by expanding the number of partitions. And as the producers write to the different topics, they're also writing to the partition. And then consumers can decide to pull from a particular partition, all the partitions, whatever they want to. This has implications for Samza later. A Samza job. Much like a MapReduce job, it has input. MapReduce jobs, the input are files on top of HDFS. Here we're going to be inputting topics from Kafka. So we can look at status update event, new connection event, like update event. We're going to have a little bit of code that you have to go and implement. And that code will then write to other topics as it goes. That's the basic anatomy of the Samza job that we're doing here. Skipping to the execution engine. How many people here are familiar with Yarn? Okay. So Yarn was basically designed after the job tracker started to fall over at Yahoo. Everybody here is familiar with how job tracker basically works, right? You submit a job to it, that job tracker is then responsible for tracking not just the job, but the individual tasks, right? So that means that as one machine grows, as people submit thousands and thousands of jobs concurrently, the job tracker is responsible for keeping track of the jobs and all those tasks. Difficult to do, doesn't scale very well. So eventually, back at Yahoo, they decided to break this up, write a new system that was more generic, and would, from the MapReduce perspective at least, allow each job tracker to actually track just the job, and therefore the job tracker is no longer a single point there. Yarn is the result of that. It stands for yet another resource negotiator. If you're familiar with Sun Grid Engine, it looks kind of like that. So it's essentially a framework for getting your code out to machines and running them. Like I said, it's what we did with the job tracker once the job tracker stopped working. But the interesting thing for us and for a lot of other frameworks is this means that the nodes that you've allocated to Hadoop are no longer just dedicated to running old-style MapReduce. Even better, they're not even just, you used to have to say, this particular resource is only for maps, this resource is only for reduces. You have a lot more freedom, right? That means that you can now write other frameworks, for instance, like Apache Giraffe, Hoya, all kinds of stuff, Samza, everything's coming open. What this means is it's going to be the wild, wild west for Yarn for the next couple of years. It's going to be very interesting. So what does Samza use Yarn for? We're actually not that innovative in how we're using Yarn. It was a very good resource that everybody's converging on, so it made sense for us to use it as well. We will take the Samza code that you give us, we will bundle it and turn it over to Yarn to distribute out to the different machines that you have in your Yarn cluster. Yarn will keep an eye on it and tell us when one of those machines has died, when one of those tasks has died. And we will then tell Yarn to go send out a new replacement for it. The other thing that we're using it for, as it matures in its ability to do this, is to isolate tasks from each other. Once you start running all kinds of different workloads on these machines with different characteristics in terms of memory, in terms of CPU, in terms of network, you want to be able to control how they interact with each other. Yarn is developing the way of doing that right now. Yarn cluster of 2 machines, how we would use it, is pretty simple. Each machine has a node manager. That's the thing that's responsible for running your code. When you write a Yarn app, you write an app master, and that's responsible for actually telling Yarn what machine, what code you want to run around. That's the thing that's always going to be running in response to, hey, this container died, what do you want me to do about it? And so in our case, we will start up the app master, and we will tell Yarn to go put a couple of processes on another machine, where we will go and run the code that you give us. One of the things that we've been doing is also putting the Kafka brokers that I talked about co-located on the machines. This kind of works, kind of doesn't. We're experimenting with if that's a good idea or not. At the moment, we don't have any way of getting locality for the data like you would say in HDFS and MapReduce, so we're not seeing a huge benefit, but we're going to look at that further. But right now, our Kafka brokers are usually on the same machine. One thing that is interesting to talk about is the way that we actually group your code together. Remember how I mentioned that Samza was partitioned? One of the things that we can do right now is that every task that's processing a partition, all of those topics will go to the same task. This effectively allows us to do a group by your partition ID. This means that, for instance, if you have a lot of different data input streams and they're all keyed on, say, the user ID, every single one of those topics for that user will go to the same bit of processing. So in this case, we have status updates and new connection updates. Partition 0 for both that, which if you do a mod hash on the PID will go on the same one. The same task will see the status updates for the same users and the new connection updates or events for the same users, and is able then to group on. Yeah?
Do you partition topics too?
Do we partition topics?
Topics partition for the machine.
So are there, the question is, are the topics partitioned on different machines? No, it depends. I mean, if you have a topic, if all of your topics have the same number of partitions, we will distribute it evenly around. If you have some topics that have more partitions, those topics will just end up on the machines that are processing those partitions that exist. So does that answer your question?
Yeah, I'm just wondering, some topic is very popular, a lot of people send it, what happens?
So if some topic is very popular, what we recommend people do is add more partitions so that we can get scale that way, horizontally. And then, yeah, we will have more partitions to process. Those will get on some other machines. We are working right now. I'm working, hopefully I'll have some code by the end of the month that gives us a lot more partitioning strategies so that we can actually do things like partitioning on the topic name or grouping on the topic name. That's coming shortly. The third bit is process. Where you used to write mappers and reducers in MapReduce, now you write a Streamcast. This is a pretty simple interface because Samza itself, as you've seen, is a pretty simple wrapper around what we've got. Essentially, we give you an envelope from which you can get the key or the message. We give you a collector, which you can send out new messages with their topic, their key, and their value. And then we give you a coordinator, which has a couple of methods. You can call commit, you can shut down if you want. That's pretty much all you actually have to write a stream task. There's other things that you may want also to do with your stream task. So there's interfaces you can implement, initables that we call you at the beginning, closable we call you at the end. If you want us to make sure that we call you every 10 seconds, you can also implement that interface. Now, the killer feature that Samza has, which we haven't seen in any other stream processing framework, is state. One of the interesting things that we can do is because we write everything out to Kafka, we can also write your state out to Kafka. So we give you an interface that's very generic at the moment. Basically, it's keys and values. It's backed by LevelDB and our current implementation. But every change that you make to that key value database that we give you, we also persist up to Kafka. Now, in the event that your application, your container crashes, we will go to that state that we've written onto Kafka, replay it against the LevelDB, and because we are using Samza and Kafka and able to move around in the streams as we want, we can basically restore your task to exactly where it was when it crashed. It might take us a couple minutes to replay the state, but we can actually have state that we will get back to you when you crash. Question?
Something similar to Trident Store.
I don't know much about Trident, but Storm doesn't have a state like this.
Store has a couple of ways to define topology.
Topologies are a little different. I mean, we don't have topologies in a Storm sense at all. But as far as I know, Storm doesn't have any way of saying, here's a local little database. If I go away, I want that database to look exactly the same as when I crashed. Like I said, we've got a key value out of the box. We're looking for more implementations.
So, Brandon, why do you use LevelDB for giving a state instead of using Kafka? Because Kafka is also somewhat key value.
LevelDB will, as long as things are going fine, the question is why do we use LevelDB instead of Kafka? We use them both, right? So you write some kind of state to LevelDB, we will write that to LevelDB, we will also play that against the Kafka log. And as long as everything is going fine, we will just use LevelDB. It's only when you actually crash that we will replay against the Kafka log to get your LevelDB back to where it was.
So, why do you use LevelDB along with things like this?
Kafka is optimized for sequential reads, so you could use it like a key value store, but it's really not meant for that, whereas something like LevelDB is optimized for key value. So, quick little example code. Let's go ahead and implement a little mini Twitter using Samza. There's two things that we'll be looking at. We'll be handling. One is a status update event. I've done something. Hey, everybody, how you doing? And what we want to do with those is we want to send it to everybody else that's on your connection list, right? Somebody updates their status on Twitter, everybody else should see it. The other event that we want to look at is a new connection event. Somebody has followed me, I followed them. So now, in the future, they should also get any new status updates that I do. So we've got a class here, newsfeed, which is implementing Streamcast. First thing we do is go ahead and get the message out of it. We use Avro pretty much exclusively at LinkedIn. So a lot of our interfaces play very well with Avro's generic record type. But this is all also typed for enterprise, so you can basically do whatever you want with it. So what we can do is we can go ahead and get the message, get the user ID out of the message, and then check what type it is. If it's a status update, we're going to go through, ask our key value store to get all of my connections. And for each one of those, we're going to send out a news update post, which will end up on their. On the other hand, maybe the event that we got was that it was the only other event that we can handle is the new update. So we get the new connection. So we get who the new connection was. We get the key value store update. We get their user, and then we replace that original value with the list that's been updated with the new value. And then the web page, the web interface is listening to these on the Kafka stream, publishes them as they come out. Any questions about that? So that's how Samza works. We've been using it at LinkedIn now for almost a year. A quick little case study of our first production app, which is what we call the call graph assembly. This is in production running at LinkedIn right now. It's worked very well. So this is what the normal LinkedIn looks. Question?
On the previous one. So I can see like that you would have for any of these cases that eventually a Kafka stream would be generated. So the web interface, is it polling something, or is there a way to notify the web?
So the web interface would have a Kafka consumer that's basically going along ahead and saying, yeah, give me everything as it comes in. And based on that, yeah, rendering from there. So they will have, however the web interface wants to do it, they'll keep a store of like the last 100 things or whatever.
Okay. And for in the very early graphs, pictures you were showing that there was an app master or an app controller, and basically using the DB and everything was to deal with the failure. If that particular node fails, you'd come back, with the checkpointing that you guys are getting, you'd be able to start from where it failed.
Correct.
Good. Thank you.
So to render a page of LinkedIn, even though it's one page, it's actually quite a lot of calls, as you might expect. Every element on there has some kind of service backing it. We want to do a few things. We want to have this page render very quickly if something's not rendering within half a second or whatever the delay is. I don't know. We'll just move on without it. But it's interesting to see all the calls that go into making one page, and this isn't all of them or even the real call. What can we actually say about all of the calls that are generated on the page? If we go and look at them, we can actually see that because LinkedIn is a very service-oriented architecture, every call is asynchronous, every call is an RPC call, every call goes off to another machine which is running that service. So there will be a machine somewhere that will tell you how many unread messages you have, that will get you your people you may know results and all of that. Each one of those machines is, because this is LinkedIn, writing out to a Kafka log. So we are generating thousands and thousands and thousands of these messages. For every call that you make onto the LinkedIn homepage, I don't know if dozens are actually emitted. Is there any way that we can get a holistic view of what's going on? We have an easy way of seeing how any particular service is working. We can just tail the log for unread message service call or whatever it is. But is there a way that we can actually join these all together so that we can see how these services are interacting with each other? If we give the first call that was made a unique identifier, and then every call that's made subsequent because of that shares that identifier, as long as they have that unique identifier, which we call the tree ID, the data is in there. It's spread across hundreds of different logs on hundreds of different machines, but we then are able to actually say, this one was all due back to that right there. So in this case, you'll notice that it actually ends up looking like a tree, right? Because there will be hundreds, dozens of calls for any particular one. In this case, it got the incredibly random number of 1, 2, 3, 4, 5, 6. Every single call that happened because of that also has 1, 2, 3, 4, 5, 6. So we can have two Samza jobs. One which will be repartitioned by tree ID. Samza Kafka messages, remember, have a key and value. The keys that are coming out of these service call logs, I don't know what they are. We don't really care. What we want is we want all the keys to be that tree ID. So we have what's called a repartition job. We take the message in, we discard whatever its original key was, its new key is going to be that tree ID. So we are consuming from hundreds of streams at the same time. Not doing very much, just taking the message in, giving it a new key, and sending it off to one big new Kafka stream called all service calls. And these, again, are then partitioned by the tree ID. So that if you are consuming one particular partition, you are guaranteed to get all of the same calls that were for that tree ID. That is then consumed by a second Samza job, which is a symbol call graph. This is just a giant window group by. This job sits there and listens. It says, ooh, new tree ID. I'm going to give it, what we found works really well, is about 3 minutes for all of the other calls that share that tree ID to show up. And once that is done, I'll do a little logic to go back and reconstruct that tree. And I can emit an actual tree-like structure that says, these are the actual calls. This one started it. They all descended from here. It doesn't always work. There's sometimes some network latency. They sometimes lose a tree ID because of some bad code or something. But in this way, we're actually able to rebuild what happened on the site within a matter of minutes when it actually did happen. This is really cool. Our tools team has built a lot of very cool stuff on this. They've got tools that will basically show you the tree, show how long each call took. They can dip it between different days. They can say, hey, all of a sudden this one just disappeared. I don't know why. They can compare it to different revisions if we check in the source code. Yeah.
So essentially, you're doing this so that your regular queries are optimized. So that usually you're looking for call graphs. You will be having them, instead of like if you had a query that was going and spanning across multiple partitions, all the data is in a single partition so that you could look at it quickly.
To do that, we do this so that you can scale. There's too many service calls. You'll notice that the name of what we're consuming here is star service call. That's literally hundreds and hundreds of service calls. And we actually have, it's a regex. Every time the job comes up, it gets the new one.
The reason I was asking that is at times we want like different kind of partitioning on the data, or like different views on the data. For example, users in a particular region, what are they doing?
Mm-hmm.
especially when you're getting a lot of calls, you want to know which users got affected because of this thing. And so in that case, would you like create another repartition thing from the streams, and maybe that would go into different partition?
Yeah, in that case, if you wanted, so there's two ways, right? One is we just want a completely different thing. We don't care about the tree IDs. The other is we care about the tree IDs, but then we want to filter further on that. So you're asking about the latter one, so that we only just want this region?
No, the former one, actually.
So the former one, where instead of the tree IDs, we're looking at something else, yeah, then you would have another repartition, a different repartition zone. And the bottom bullet there is that this looks a lot like a map reduce job if you squint at it just right. This is going to be a common pattern. The data is coming in some way. We have to repartition it so that the reducers, or the second job, get the right data. So repartition group is going to be a very common pattern. We'll see what the Samza does. So that's the system, how it works. Quick little use case that we have at LinkedIn. Samza is an Apache project. How many people here have worked with the Apache Software Foundation before? Apache is a very cool organization. We have more than 100 top-level projects. Those are the big ones. Everybody here is probably familiar with Hadoop, Hive, Pig, HBase, Cumulo, all of those. The granddaddy of them all, of course, is HTTP. It's collaborative open source engineering from all around the world. When you want to go and take a chunk of code like this and donate it to Apache, you have to go through basically what's a probationary period that's called incubator. And that's where they say, okay, you can come into Apache, but you have to prove that you guys know what you're doing and can work with our rules, the Apache way. In that case, you get to basically be a little mini project for 3 months, 6 months, a year. And then if you demonstrate that you have built a sustainable community around the code that's not just from the original contributors, then you get to go and graduate, be a top-level project like the Duke employees. We are in that stage now. We gave the code, we donated the code 6 months ago or so. So we are in an active mode of looking for new contributors, looking for people that want to make the code better. If this is something interesting to you, if you wanted to get involved in open source, this is a great way to do it. We are extremely friendly. We have, I think, the best documentation of any open source project out there. Chris Riccomini, the guy that started this, just loves to write documentation. So when I get the inevitable Samza versus Storm question, I'm going to direct you mainly to the documentation because it's really awesome. The other thing that we do in order to make sure that this is a friendly environment for people that are getting into this and haven't maybe done open source before is we maintain a set of issues that are we call newbie issues. These are simple pieces of code. If you are a software engineer, this will insult your intelligence. But it's not designed to be the greatest thing. You're not going to win the Turing Award. This is fixing a typo. This is fixing a spelling mistake. This is, changing a variable, something like that. It's designed to get you into Apache, get you to clone out the repo, make a change, submit a patch, work with the community, and then after you've done one or two of these, you can actually start taking on meatier things. We keep a list of those at Samza Newbie Issues. And check today, there are definitely some still there. So if you want to get into open source, this is a great way to do it. The other thing that we've got is a GitHub project called Hello Samza. Right before I came up, I checked and this wasn't working. But I'll get it working. And it's really awesome once it's working. We got a cool pull request from Joel Stein over in, who's a Kafka committer. So basically what we do is we actually, when you clone this, we will set up Yarn for you, we will set up Zookeeper for you, we will set up Kafka for you. And then, I didn't know this before Chris wrote this, but there is an IRC channel where all edits to Wikipedia are published as IRC comments. So this code actually treats that as a stream, consumes those changes, and processes them, sends them to a Kafka log. A second job starts up and then starts running statistics on them, the size of the changes, who did it, and all of that. It's really cool. We got a patch just a couple days ago from Joel Stein that instead of having to do this all yourself, he moved it to Vagrant, which I'm not familiar with, but looks very cool, except that it broke the other code. So this is really cool, and we'll have it back up and running quickly. But if you want to see how Samza works, this is a great way to do it. That's all of that I've got. One thing that I would strongly recommend is our principal staff engineer and my boss, a guy named Jay Krebs, wrote a very cool blog post / novella, pretty long, about logs. what we're doing with it, what we're trying to do with it. Samza plays a huge role in that. Kafka plays a huge role in it. It's a very interesting way of looking at logs and their role inside of any kind of big data organization. I really recommend everybody go and take the time to read it. It's really good. Other than that, come join us. We're looking for contributors. We want to make this as good as possible. Thank you.